Hey everyone, let's do a problem similar to the one we did in class. For number 16, let's show that the equation ax equals b does not have a solution for all possible b, which is the same as saying that the column vectors of a do not span R3. Instead, we want to describe the set of all b for which ax equals b does have a solution. Okay? Now note that if we just wanted to see whether the vectors of A, the column vectors, spanned R3, all we would do is row reduce the matrix and see whether there was a pivot in each row. If there were, then it would span R3. If not, then it wouldn't. But they're asking for the solution set, so that requires a little bit more work. So we're going to write the augmented matrix, keep track of these B1, B2s, B3s. And we're going to row reduce, and let's just see what happens, right? Now we're going to follow the standard row reduction formula, right? 3R1 plus R2, right? I'm going to do negative 5R1 plus R3, etc. So that'll be a 0. That'll be a negative 7. Negative 6, and then 3R1 plus R2, so we're going to get 3B1 plus B2. Then we're going to get, right, this stays the same, I guess, whatever. Okay, and then, of course, to continue along, right, negative 5R1 plus R3. 1, 0, well, I guess I'll just do 4. B1, this stays the same. Right, and then this becomes a 0. This becomes 14, 12, and then we have, what are we going to have? Negative 5R1, so I think it's going to be negative 5B1 plus B3. Let's do that. Now notice, oh, that's pretty nice. We can just turn that into a bunch of zeros. So what we're going to do over here, I think I can squeeze it into this matrix over here. 1, negative 3, negative 4. This will be B1, 0, negative 7, negative 6, 3B1 plus B2. Now here what we're going to have, this should just be a row of zeros, right? Because we're doing not even negative, right? I guess just 2R2 plus R3. Right, that should do it for us. So what that's going to give us here is going to give us B1, right, because it's 2 times 3B1 plus 2 times B2. Right, so it's going to give us B1 plus 2B2 plus B3. Okay? Now, we don't need to get hung up with the x's because we don't actually need to find the solutions, x1, x2, x3. The way, for example, in my previous video, I did find solutions for x1 and x2 with the Iola problem. Here, though, we're more interested in the solution set. What are the vectors b1, b2, b3 that are solutions? Forget about what x vectors they correspond to. In particular, note this. We need B1 plus 2B2 plus B3 to equal 0. Or, in other words, B1 to equal negative 2B2 minus B3. Now, in this case, note that B2 and B3 can be whatever they want, right? So you could look at this as, well, letting B2 equal some constant S and maybe B3 equals some constant T. Right, these are just real numbers. Well, then we see that our solution set is the following. it's going to be the set of vectors negative 2s minus t, s, t. You see what we did there, right? Negative 2b2 minus b3. That's b1. Just to be clear, right? This. Well, maybe I'll choose a different color. This corresponds to this, 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 I guess, this, okay? Right, and we're assuming that I guess we put a bar here, S and T are in the reals. Now, equivalently, we could write it this way. We could write this as the vectors negative 2s, s0 plus negative t, 0, t for s and t in the reals. And if we wanted to write that a slightly different way, we could actually write it like this. We could pull out the s. Let's talk about s times the vector negative 2, 1, 0 plus t times the vector negative 1, 0, 1 for s and t in R. Whew. Okay, now what exactly does this look like? This is actually a plane in R2. Whoop, sorry about that. This is a plane in R2, right? We could have, or I should say, sorry, a plane in R3. This is a plane in R3, a two-dimensional plane in 3 dimensions, right? So if we, I guess I'll call this x1, x2, and x3, then we can talk about a certain kind of plane that just, maybe I'll use a different color for this. Like this. And the two vectors that determine it are these guys. Actually, I guess maybe I should be a little more careful, right? The two vectors that determine it, this plane goes through the origin. All right. Well, it's totally clear, but plane goes through the origin. There you go. And the vectors that determine it are the vectors negative 2, 1, 0 and negative 1, 0, 1. Perhaps they look like, you know, that and that. Actually, perhaps a slightly nicer way to draw it might be this and that, and they determine this plane.